Hello and welcome. This recording is session 4 of an 8-part series on the topic Moving Towards Improved Earthquake Performance and Resilience for New Buildings. My name is John Sherstobitoff. I'm a structural engineer focusing on earthquake engineering for buildings. This series of recordings is part of the MBAR initiative by BC Housing. MBAR includes and promotes the consideration of resilience for new buildings for natural disasters such as earthquakes. The list of 8 sessions is noted on this slide for your future reference, and this was described in the original session. So today's session on supplemental energy dissipation, SED, also commonly referred to as dampers. There's a large variety of SED devices that are readily available in the marketplace, and these function and dissipate the earthquake's energy by relative movement of the damper, so there has to be movement. An example on the left is the dampers installed in the diagonal bracing in a building. In the center illustration, a pair of dampers at the top of a chevron brace. So as one floor moves relative to the other, the dampers are initiated and dissipate the energy. A common system is rocking walls, the use of CLT, cross-laminated timber, or concrete, and as these walls rock, the dampers on each edge are extended and then contract, and again, the earthquake's energy is dissipated in the dampers at each edge of rocking walls. In a previous session, there was reference to the engineering design response spectrum, and that's shown in the illustration where the base shear is on the y-axis, so the design lateral load of a building as a function of period on the x-axis. What these devices do is they increase the inherent damping in the building from typically 5% to over 30%. And what that does is it drops that response spectrum down, so that top red dot for a normal building to that lower red dot, so you can see there that the design base shear is reduced to perhaps half of that of a conventional building. What this results in is reduced cost of the structural system. Previously, I noted this spectrum of performance as far as damage or loss and time out of service. The performance target for buildings with energy dissipation or dampers is no structural damage. And you can see on the blue arrow there, the goal is to have a function that is better than immediate occupancy, close to operational, for the full 2% and 50-year code level earthquake. So again, as I mentioned, there's a lot of dampers available in the market today. What I've listed in the left-hand column are 5 common types of dampers that are used today, and on the right, vendors that really serve the North American market well. Fluid viscous dampers made by Taylor Devices. Viscous wall dampers by Dynamic Isolation Systems. Viscoelastic dampers by Kinetica. Friction dampers, 2 firms, Tectonis, QuakeTech, and metallic yielding dampers by a firm called Cast Connects. So here's some illustrations of viscous fluid dampers in buildings. So viscous fluid dampers are like the shock absorbers in your car. As the ends of the dampers move relative to each other, the earthquake's energy is dissipated in heat in that damper. And again, you can see in the building there in steel bracing, as was illustrated in that cartoon previously, or a concrete building on the right where the dampers are a small device at the base of each brace. Metallic yielding dampers. Again, these are just pieces of steel cut to a certain size and shape. And again, all the earthquake's energy is dissipated in yielding of these devices, leaving the structural system intact and undamaged. On the right side is a picture of those dampers covered with that red protective coating on those in that steel bracing in that building. Viscous wall dampers. This is where a steel plate is inserted inside a steel box. So in the image on the left, the top plate is connected to the upper floor, the box is connected to the lower floor, and there's a very viscous fluid in between them. And as the plate inside the box moves back and forth, left to right, the earthquake's energy is dissipated through heating up of that viscous fluid. And this has been used in a very large hospital in San Francisco recently. Viscoelastic dampers are similar. In the photo on the left, again, one steel plate between two other plates, and as that one plate moves side to side in between the other plates, the viscoelastic medium in between dissipates the earthquake's energy. On the right, in new buildings nowadays, of viscoelastic coupling beams in yellow, again, there's a series of plates that slide past each other with the viscoelastic material in between, and that dissipates the earthquake's energy again to leave the remaining structure undamaged. Friction dampers. This is similar to the brakes in your car. You know, one piece of material on another piece of metal in friction, dissipating the earthquake's energy. So as these devices are extended and contracted, and metallized plates or specific material, proprietary material, slide past each other, the earthquake's energy is dissipated in heat as these plates slide relative to each other, typically installed in a bracing configuration in buildings. And as I mentioned earlier, rocking walls is becoming more common. On the left, a concrete wall with friction dampers at each end, and as the wall rocks back and forth, and these devices extend and contract, the earthquake's energy is dissipated in those devices, and CLT walls on the right, similarly the devices installed at each end. And this is becoming more common. So in the building codes today, again, these are fully prescribed in current codes, BCBC 2018, the Vancouver Building Bylaw, and the National Building Code 2015 and the newly released 2020 version. 3D nonlinear dynamic analysis is required. 2 suites of 11 earthquake ground motions are simulated in the analysis. And again, these devices are modeled for the expected variations in their properties over the design life. The good thing about these devices, prototype testing is required for a minimum of 2 full-size specimens to make sure the real product reflects the analysis. And similarly, for the production testing, before the devices are sent to a site, a representative sample of these need to be tested to confirm that they're within the properties that have been designed and analyzed. And again, the code requires that there's access for inspection and replacement of these devices should they need to do so. However, they're designed to function earthquake after earthquake with no loss of performance and no need for replacement. But again, it's nice to have a look at these after the earthquake. Again, all buildings with these devices have to, of course, sustain the wind load with the very same minimal deflection as a conventional building. And again, every building is designed for the mean plus standard deviation, so a certain a demand on the building. So again, not just the average demand, but a higher demand on all the existing structural components to make sure they remain elastic or undamaged. So again, this is a high level of demand on the buildings to confirm that they remain elastic for the code level earthquake with these devices. In addition to that, the existing structural components have to have a modest level of ductility detailing should the actual earthquake be significantly larger than the code earthquake. So a bit of robustness built in as well. So some general considerations. These also reduce the interstory drift, the deflections, and the demand to non-structural components. The vendors that I listed before provide excellent technical assistance to the structural engineering community. One can consider fire protection of these devices to ensure their capability to sustain aftershocks, which usually happen should there be any fire following after the earthquake. And again, as engineers, we can specify a specific product for use in a building, or we can provide a performance specification which allows bidding by a variety of vendors to achieve that given performance in a building of no structural damage with all the energy dissipated by these devices. So in summary, there's very good provisions in current codes to design and implement these in new buildings. It's now proven, it's been used in many countries around the world, and now some buildings in BC and parts of Eastern Canada as well. The intent is to provide no structural damage performance for the code level earthquake. Again, that reduced demand and damage to the non-structural components in a building. It does require more analyses at the beginning in the engineering phase. And it does require special attention to detail to accommodate the deformations at the location of these devices, because deformation is what drives the energy dissipation, so it needs to be very carefully considered. So that concludes this session. The next session will focus on the costs for improved performance of new buildings. If you would like more information on this topic, please contact me at the email address noted below. For more information on MBAR, there's an email and webpage address noted. Thank you for attending this session, and I hope you join me again for more sessions in this series.